Hello everyone. Today I have the pleasure to present you our AGU contribution examining the uncertainty estimation properties of LSTM-based rainfall-runoff models. My name is Daniel and this is joint work with Frederik Kratzert, Martin Gauch, Alden, Sampson, Sepp, Hochreiter and Graineering. The plan for today is the following. We will go through the title in reverse order, starting with LSTM-based rainfall-runoff models in general. Then I will show you how we can expand them to provide uncertainty estimations. And lastly, I will show you how we can probe those uncertainty estimations to examine their properties. So let's not waste time. LSTM-based rainfall runoff models are quite special for me. In general, when we think about environmental modeling, we try to take a broad data-driven view and not restrict ourselves to special methods. LSTMs are, however, special because of the relationship to the conceptual model. In the following, I will show you what I mean by that. So this is a conceptual model called Coursera. It's a HPV-like conceptual model, semi-distributed. I used it for my PhD. And with this and with many other models which are similar in structure, we can write them in a state space form. Basically, you see two equations. One translates the states to time, and the other set of equations takes the states and generates runoff or stream flow or and general environmental flows from it. Now if you juxtapose this with the LSTM, you see it's quite similar. Now the LSTM has two forms of states, the cell state C and the hidden states H, but again we have two forms of equation. So this parallel form that you see here basically motivated our first paper, which is the first LSTM paper by Frederik, in which we examined if it's even possible to use this LSTM for rainfall runoff modeling. And spoiler, it was, of course. We also conceptualized if it is possible, or if it would be possible, to relate the cell states with environmental flows or observations or other states of the hydrological models. And it was, but it was still not very formal. We later tried to formalize this in a book chapter, where we tried to interpret the cell state and really look at what information is in there. And this duality between building models and examining models, which you also saw in this title, is something quite typical for our research. Anyhow, from this paper, a lot of other contributions followed, so that we now decided to collect them all in a research blog, which I encourage you to go. And here on the left, you see three papers which are good to start with. The one from Frederik is nice if you're coming from the hydrological side. The one from Martin is nice if you're coming from a data scientist or computer scientist side. And the one from Gray is I think, cool if you're interested in the big picture. If you want to see what kind of flavor of models we are thinking about de facto in reality, I recommend our work in regionalization and prediction in engaged basin. Lastly, if you want to see how we would try to expand this, I can recommend you another AGU talk by Martin, which is about how we can leverage multiple timescales with the LSTMs. There is also now a discussion paper out, so I encourage you to read it. Now, all the studies that I showed you in the previous slide, what they have in common is that they use point predictions. Now, I will use that to motivate the uncertainty, which is like the second part of this talk. So uncertainty estimation, what do I mean when I say point prediction? Here on the right, in the upmost plot, you see a prediction for a single time step, and it's just one point, and we compare it to another point, which is our observation. So this is a point prediction. There are then higher forms of predictions, if you want, which give us more information, because they also provide us information of the uncertainty. So below you see prediction intervals, in this case the 50 and the 90% prediction intervals. And then below you see the distributional prediction, which gives us the full information of the distribution. So what I did here actually is I took this prediction intervals and the mean of the distribution and generated the lower order predictions from it. And what I like that you acknowledge is, or that you see, is that the observation, if you just have the first one, it's difficult to say anything about observation. If you have the B, the second one, you can see, okay, it's still within our, what we would expect is just an unlikely value, perhaps. If you do, however, have information about the full prediction, like in the last one, you see that the mode or the maximum likelihood is actually quite near the observation. It's just that the distribution is very skewed, and thus it lies so far outside. the overall distribution. So distributions are awesome. If you think about this in kinds of types of predictions, you obviously want to have distribution. Now, this is not always easy, and I think a reason why many hydrologists do not think about it in terms of a type of prediction is, again, the model structure. So if you look at the model structure, usually what we do is when we make our modules, we think about it in terms of concepts and processes in the environment, and we don't think about representations that are made to represent the stochasticity or the uncertainty. So there's no, usually we don't have an explicit representation for uncertainty. Usually we have a deterministic model, and then we attach some kind of second structure to it, or some second approach to it, to get uncertainty out of it. Like we use ensembles, or we use post-processors, pre-processors, some data assimilation scheme, heuristics. Very seldom use some stochastic differential equations in front of it. And all this we do just because we don't have this uncertainty representation. And it's here where data-driven approaches, or LSTM in this case, is really powerful, because we can exploit in the training certain attributes of it to get uncertainty out, or we can even tell him that the y is uncertain in nature, and then it will learn from alone uncertainty represent. In both cases, it will learn from alone uncertain. That's not alone, but it will learn uncertainty predictions just by the nature of the training that we impose on it. So we have then representations which are built to and learn to give us uncertainty estimates. In the following, I will show you two concepts, two approaches to get to this. So Monte Carlo dropout is the first one. It's based on dropout. Dropout is a very famous regularization techniques for neural networks. And here on the right, you see it illustrated. So in plot A, you see the full network, and what you do during training is you randomly drop out certain components of your network. What then happens is that the network will have to learn an implicit ensemble, if you want so. And what these two researchers here at the bottom showed is that if you sample from it repeatedly, so you let it run and then run again after the training, and always drop out different components, you can use this to get the uncertainty estimate. So I looked at this last year at the AGU, and what you see here is a hydrograph, and in yellow you see the MC dropout ensemble, where I resampled at each time step 100 times. And in green you see 100 different LSTMs trained on the data and run in parallel. With both, you always see the minimum and the maximum value for each time step that I obtained. And what you see is, albeit the Monte Carlo dropout does not cover the ensemble completely, it covers large parts of it, which is quite impressive, I have to say. Second option. So mixture density network are our second option, and here is we tell the model explicitly that it should generate a conditional distribution. So the idea is the following. We have an input to our neural networks, like rainfall and temperature, and then we estimate from that parameters of several density components, for example 3 Gaussians, like here, and weights, and the weights tell us how they are mixed together. And then we get a conditional density in this case, so given this rainfall and temperature, we will have a conditional density which is a mixture of the simpler densities, which provides us the runoff estimation. Now let me give you a bit of an intuition for that. So here on the left in plot A, you see 3 different components, 3 different Gaussians, with different means and different variances. And below in plot B, you see this Gaussian mixed together with different weights. So here the blue one, the middle one, has the highest weights, and the other ones has lower weights. In C, you see the same component, but mixed together with different weights. So here the red one, the left one, has the highest weight now. And what you already can see here is that we can model a lot of different new densities by mixing those components together. Now the neural network does de facto more, because it will also estimate our variances and our means, or actually the parameters of whichever components we give it as a distribution. Now, this brings me to the next part. We don't have to stop here. We don't have to use Gaussian. So for us, a logical alternative was a Laplace distribution. which is also often referred to as double exponential. Because from our previous studies and from working with conceptual models, we knew that when doing simulation, we will often have a lot of small errors and then some big errors. So there are a lot of reasons why this happens. One is, of course, the nonlinearity of the system. And you don't want to have a function with thicker tails than a Laplace function, because if you would have that, then it also means that you will not be able to really properly model the system. It's very unlikely. We can go even further. So a researcher called Bonder proposed to use asymmetric Laplace functions as components. Then you have a new kind of parameter that you have to estimate, which tells you the skewness. So here below on the left B is a different skewness. So I have an additional parameter to adjust the skewness of the distribution. And we thought this might be extremely useful for us because especially for smaller river, we often are near this the zero cutoff, if you want so, because there is not possible to have less than zero runoff, obviously, but the distribution is defined over almost all space. So if it can skew it, we thought it would be very easier to model it. So there's a trade-off, more parameters, but you have a component which more closely reflects our system. So we collect all of this, we compare different methods, and do quite of a benchmarking, all in a paper. The paper is not yet finished. We hoped to have a preprint out by AGU, so check the question and answer session. We will link it there or Google for it. It should be finished by then. And we do also many more stuff that I cannot show you now. So I will hold it here and use the last 2 minutes to show you a bit how we can potentially even examine now this uncertainty estimation, because they natively come out of the model. So take this model. So we have this mixture of densities. This might be how it looks. So what you see here is a hydrograph, and you see again as before the 50 and 90% quantiles superimposed, and we took them from a mixture of densities by evaluating each step and then check out where the limits are. Please note again what we said before, there is no value below zero, and we also have like an asymmetric behavior going on here. So quite nice. This is what you would want. Now often in research and as a hydrologist you would say, well, but this now assumes that the network is able to perfectly estimate the parameters of this distribution. This might not be the case, for example, because the input is uncertain. Now this already uses an ensemble of inputs, but you could still theoretically define, for example, a noise pattern. But then you have to think, well, and what would be the noise model of our input that we use to contaminate it with? So I think I would like to propose an easier way, a more straightforward way to see how the uncertainty will influence the parameters, and that's by using MC dropout on top of the mixture density network. So to illustrate how this could work, look at this slide. So on the left is a different basin, slightly different situation, and the 3 ovals mark 3 points where I capture the density. So below you see in red the 3 densities corresponding to these 3 ovals marked points. Now note that I rotated them so that they correspond to the runoff, and note also that the y-axis is not fixed, so these are actually quite different y-axes. Then I used MC dropout to sample from these points. So what happens is I re-execute the model, but drop some components out, and it still has to estimate the parameters. But it has learned already that how it can compensate them somehow. And here in light gray, dark red, superimposed in the densities, you can see how they change. And so this is now an approach to examine the uncertainty of the uncertainty, basically. Or would be an approach for that. So I finish with that. Again, here is my research blog, or our research blog. You can contact us. We are quite open and happy to collaborate. I did show you like basically rainfall-runoff modeling with LSTMs, how we can obtain uncertainty estimates from them, and even that it is possible to probe those uncertainty estimates and check for higher order uncertainties or other kind of properties.